So you can call me Tam for short. I work at Cake Solutions. So Cake Solutions used to be a consultancy, but now it got acquired by BAMTech Media. That's why I'm wearing a different T-shirt. So BAMTech Media is a video streaming company that also got acquired recently by Disney. So that's explain why we have Mickey Mouse on top of our booth. All right, so today I'm going to be talking about new features that landed in Scala 2.13. Specifically, I'm going to be talking about literal types. So my agenda for today is, first I'm going to get everybody up to speed. I'm going to be explaining what's singleton types, what's literal types, and a couple of highlights from the recent pull request. Then part two of the talk, the interesting bit, I'm going to be talking about 3 use cases for literal types. The first one is the practical one. I'm going to be talking about a library called Refinement and how it can help you to write better programs. The second 2 use cases, those are research projects of mine, so that's why they're not practical. The second one is about encoding SQL queries as literal types to make sure that you can prevent SQL injection happening. Last one is a bit more involved, so it's using literal types as well as other type system features so that I can understand my SQL query at compile time. And for example, if I'm selecting a column that doesn't exist, I can get compiler error message telling me, oh, like this column is not there. All right, so let's start. All right, so let's first talk about singleton types. So they exist almost in any Scala code base. For example, consider this object definition. What would be the type of this object? Like the type doesn't extend. There's no extend syntax or anything here. So you can say it's an instance of any or any ref, but there is also one more hidden type that you can access via the syntax object or path dot type. So this is basically a type that has one single instance, in this case, the object itself. This is just one form of singleton type. There is other forms of singleton types that the compiler is capable of representing. For example, the number 42. The type system is also capable of having a type representation for this value, even before 2.13. However, before 2.13, there was no syntax to use it. So the feature was pretty much like a beast in a cage. Like you can't interact with it unless you use something like shapeless, which kind of invents syntax for you to use literal types. So this line basically means we are having a function that can accept only 42. And if you pass anything else, this is a compile error. The news in 2.13 is now we have better syntax to achieve the same without shapeless. So you can write this now in 2.13. It will be exactly the same. So 42 in the position of type here means the singleton type that has only one value, 42. And of course, if you pass something else, this is not going to compile. If you want to try this out, you can via SBT. Just jump to M3 version. You will have access to this feature and also a couple of other features that I'm going to highlight 2 more of them. So what else we got in 2.13? We got a way to hack the way type inference works. So by default, if we pass here the value 42, the type inference will infer t as an int, even though in 2.13 there is now the type 42. It's more specific, but the type inference doesn't like to infer it. This didn't change. The way you can force the type inference to pick the narrow one is by passing here upper bound of singleton. So this means the value here has to be literal value, and it will pick the most narrow type 42. Okay? One also other cool use case of this singleton is if you mix it with like string, for example, you will be able to write a function that accepts only hard-coded values, but not runtime values. And we will see this specific example in one of the use cases. The last highlight is the ability of jumping from the type level to the value level. So if you have 42 here as a type, so this value of is function that is part of Scala now. By calling it, passing the type parameter, it will give you back the value associated with it. You can either call it directly if you know the type like that, or if you have type T, type parameter or something, you can also call it, but you have to propagate the evidence. So the value of with a capital V is the type class, the magic type class that the compiler creates the instances for you. This value of doesn't only work with literal types, but also work with other singleton types like objects and even unit as well. Okay, this is the end of the part 1. Now I'll be talking about the interesting part, hopefully. So first use case, I'm going to talk about refinement types, the practical use case, as I've said. So let's consider this use case. We have an application. Our application connects to a database, and we accept the database endpoint as environment variable. We have this data structure to represent the host name and port. We have a method that looks like it reads the configuration from the environment variable and returns an instance of endpoint. Also from the signature, because it's an either, so I can guess it does some sort of validation for me. Then the rest of my application, I'm using an instance of endpoint to do things with it. So far, so good, but the problem here is int is a very large, has a very large range. Could be negative numbers, could be very big numbers, numbers that are not valid ports. So even though this function looks like it validates, first thing, I'm not sure if it validates correctly or not. The type signature doesn't tell me if it checks for negative numbers or not. Maybe it checks that's a valid int or so. So there is a solution for that, a library called Refined. So by having some imports, we'll be able to have a more specific type. Like, for example, we can encode sort of validation or restrictions as type information. So literal types here used in a type position to write any regular expression you can think of. Port as well is represented as range of numbers. If you have the information hard-coded in your code base, there is some macros for you, so you can write it directly and get compile time error message if you wrote a wrong value. But if the value is runtime value, which is most of the cases, you get for free a method that validates the input for you, gives you either write with the value or the error message as a string. So validation code for free, basically. So now by using this into our case classes, we got 3 things. At least 3 things. So first, we got more type safety. We are now sure anywhere we use the instance of endpoint that it has a correct port. We got validation code for free. And one more thing I'm going to show, you can even get parsers for these types for free. So I'm going to talk about a parser library called Atto. So this is how you normally write parser. So here we're like accepting like host name, which is like letters or digits, then colon separator, then a number, int. So this code doesn't have the same validations we have wrote in our refinement types. So instead of repeating things and also putting the validations here, you can just use the same refined types. So this is a recent integration. Oh, I have okay, problem. Anyway, so this recent integration allow us to just put the restrictions here as type parameters. Then you'll get here your refinement types as output of the parser. So passing correct port give us the instance of endpoint with the refinement types. If you pass something wrong, you will get the same error message you got from refine v, but this time it's part of the big parser. So this was the first use case. Now, the next two use cases are the experimental or research projects I have been working on. And the last one, I'm going to show a weird hack. So, preventing SQL injection at compile time. I'm always a fan of encoding or writing my queries as raw strings like that so that I can copy it to the SQL console or whatever. But the problem with this is that it's so easy for you to forget and start concatenating with input instead of delegating this to the database. So very simple project idea that I thought of. So how about just using literal types to write something that wraps all my queries to make sure it always has to be hard-coded, like you can't by mistake do it unless you'll have a compile error. So this works as expected, but the limitation we got here is we lost also the flexibility of concatenating with other literal strings. So I can't now say, oh, query 2 is the same as query 1, but with one more clause or one more thing. So I lost this. However, I found a library. I didn't know about it like about a few months ago. I just learned about a library called Singleton Ops. It should allow us to somehow magically concatenate types. Sorry, I need more water. So by importing this library, we have access to a couple of utility type classes and utility type aliases. The first utility we're going to use is just alias for a string with singleton to become X string. Just type alias to save space on the slides. That's it. So let's see how we're going to use singleton ops to concatenate literal types at compile time. So let's define this colon plus method. So the method accepts another type parameter, q2, that has to be as well literal string. Then the output somehow should be the concatenation of those two types. So singleton ops allows you to write this. So while this looks like we are adding types or something, it's not. Behind the scenes, this is just a type alias called plus, just to fake the plus operator or whatever. So in fact, this is what you are creating here. It's just type called op macro that just contains the fragments of the query and the operator, the plus operator you want to do with those fragments. So now since we are instantiating something here, or sorry, the type here is not X string, so we'll have to remove the type bound as well so that the code will compile. All right, so this works so far. I'm recording fragments of the query. Each part of the fragment is literal, hard-coded string. Now, at some point, I will need to extract the query as one piece in order to execute it or do something useful with it. So we have in the library a type class called saveString. This allows us to also jump from the type level to the value level. It supports literal strings or this op macro thing. So by calling .value here, we're gonna be asking for an implicit instance of saveString of op macro of whatever. This will kick in a bunch of implicit derivations. Some of them are implementing using macros. So concatenation is gonna happen at compile time using macro. So it's still safe. We don't have problems. So we're not concatenating in runtime. And that's the use case. The last use case, this one is a bit more involved. So I'm using here, so the aim of this use case first, I want to be able to write an SQL driver that understands a bit of my schema. So if I select a column that doesn't exist, I want to get like, oh, this column's not there, or the type doesn't match your case class. So this is how I represent the schema. So every column in my schema is an implicit instance. Column names here are represented as literal types. And finally, the column types themselves here are a bunch of seal traits represented for created for every type in my database. On the other hand, queries are represented as types. So select here is a type, like a trait with just type parameters, no values. The selection, so here I'm selecting ID, Untitled. This is an H list of literal types. And the table name is literal string as well. And this is how I represent the query, the clause. So now I will show you this working. Then I will go back to the slides and explain how this was implemented. Right. So on the code here, the schema is a bit more involved. So the table names are there, but ignore them. It's just the column names here, post title, and the type's text, and so on. So here's our schema, the implicits. And here's my select statement, H list of columns, and the table name, and the relation is a bit different from the slides, but you get the idea. So let's do something here. So reviewer name is camel case. I want to fix it to be lowercase. So now I get from the compiler error message that says column reviewer name doesn't exist in table posts. So I will fix this now by changing the schema as well, and by saving, the code compiles back again. All right, back to our slides. All right, so now I'll be explaining just small snippets how this was implemented. So as a first, let's build something a bit smaller. I want to implement a sort of codec registry. So I want my driver to know about the database types and the associated Scala types for them. So for example, something like integer, the type system should be aware that, oh, it has to be int without specifying this information manually. So in order to achieve this, we define a type class with two type information. The column type is represented as a type parameter, and the Scala type is represented as a type member. And the reason that one of them is a member, one of them is a parameter, so this is because of the way I want to use the type class. So for example here, I'm specifying to the type system, I'm saying to the type system an integer. I'm giving it the column type. So what I give to the type system goes as in the parameter list. What the type system tells me here, so type system tells me int, so this goes to the body of the type class. And also the logic of decode goes to the body of the type class. Then we define instances for this decoder. So here, saying that integer goes to int, and every combination I should create an instance as well. Now, by using this type class, so we just define a method that accepts an implicit instance of this type class. Then here, by passing integer, I get 42, and passing text, I got string full bar. So I can claim here that the type system understands the relation between database types and Scala types. All right? So let's level up. Let's do the same example, but instead of specifying the database types, I want to specify column names. So in order to do that, first I want the type system to be able to know the relation between column names and the database types. So for this, also the same trick. I define a type class with type member. The input here is the column name, and the output is the column type. And this is how I define the schema, just implicit instances for every column I have in the database. Now we got two type classes. Think of them as type level functions. So column has type is something that goes from columns to column types, and the decoder goes from column types to Scala type. We can just compose them together and create one bigger type class that goes from column names to the Scala types on one go. And to define how this derivation of column decoder works, so we basically ask the type system for two implicit instances, one for the column type and the other for the decoder, and whatever Scala type we found inside, whatever database type we found in the column, we pass it here to the decoder as input, then we get back the decoder instance. Just one small fix I have to do in this slide before I move on. It's not correct Scala syntax to refer to column type here in the same parameter list. This should be fixed in Dotty because we're going to have multiple implicit parameters. But for now, the workaround is to define another type parameter C. Then here, instead of asking an instance of just n, we also specify that the type member should be the same as C. Then here we can refer to the type as C. It's just a weird hack, but hopefully you will not need to do it in Scala 3. Finally, we can write our decode function to accept X string, then give us directly the Scala type, and it works as expected. So now the compiler knows about ID, that's 42, and column title, that is like string. All right, so far so good. One more improvement to this. So I want, instead of decoding or selecting one column, I want to be able to select multiple columns, because this is normally how we do select statements. So in order to do this, I use HList to represent a list of column names on the type level. And we have a type decoder very similar to the ones we have written before, but the input is now HList of column names, and the output is HList of Scala types, and the decode functions should return this out for you. The instances for this type class is going to be very similar to how you do recursion. So in recursion, you normally think first of the base class. The base class case here is what if the input is empty. So if the H list is just empty, you return an empty list and there's no decode logic to write, just return an empty H list. But if it's not empty, you do something on the head and something on the tail. So we define head to be any type and tail to be H list. Then we define the decoder for head const tail. Ask the type system for the compiler for 2 implicit instances, column decoder for the head and row decoder for tail. So here's the recursive bit. And the instance is defined as just you compose the types we got from the implicit instances. Right, so I'm almost done. I guess I'm ahead of time here. One last thing I want to talk about is I showed you in the compiler in the demo when I wrote something wrong, review name or whatever, I got the error message to show exactly which column failed. So this was not a very straightforward feature to implement. And first, before explaining how this works, I want to explain how normal implicit errors works. So if we ask the compiler for implicit instance of free decoder of something like this, the derivation is written in like a pyramid shape. So we have to find first instance for column decoder, then column decoder has to find an instance for column has type. We know here that the problematic type is this one, blah. But the type system doesn't give you this information that easy. So all you get is just the whole big thing doesn't exist. You lose the context. So in order to work around this, I have made sort of trick. You might like it or not. So I changed it column has type. Instead of the output type being just the happy path, the column type, it's now an either. And the error is the left. We'll see now how we write errors. And on the right, the column type that you expect. In the happy path, this is how you define the instance. So write, and the integer here is inside the type information of write. In case of failures, so if that column doesn't exist, we have a low-level instance defined in the companion object of the type class that basically says, oh, this column C not found, and this plus is, I've showed before, just the fake concatenation from refined ops. So now this is the lower level of the type class derivation. Now we have instances for both cases. Going more up in the pyramid, so we have to also now all the type classes that depends on that one has to also have the output as either. And you have to define instances for the happy path and the unhappy path. So for the happy path, here, if we found an instance that has type right, then the output is also right. If not, if there is a failure, then you have to also define an instance for it. So if it's a left, you just propagate the same error message or change it if you want or add to it. Finally, towards the top of the pyramid, we want to extract the happy path only. We want to know the right side of the either. So we have this type class get. So if it was a right, then you get type out as T. If not, Then we have another implicit that is backed by a macro that extracts the error message out of the type information, then show it to you as we have seen in the demo. Right, so that's the end of my slides. I'm gonna just show you a couple of links. So this talk has more in details explanation of the last use case. This is also another version of the talk, but it's more advanced even, so more details, but the video is not released yet. Hello, John. John, I'm talking about you. Oh, the video is not released yet, so ask him for the video. Thank you. All right, here's the code for the 2 use cases I've shown if you want to have a look on GitHub. And here's the libraries I've used in the slides. And now, any questions? Thank you.
Hello. How are you going to represent more complex SQL queries with such approach?
All right. I have in the demo a bit more sophisticated representation for queries, so I can represent also operators, like for example, when you say like title equal question mark, so I can also understand what's the operators. If the column, for example, was a list of integers, for example, I can know that if the operator is contains, so I can tell you, oh, the question mark type should be the type T inside the list. It's all just writing more type level derivations. It's a bit hairy to write, yes, but yeah, it's possible to do.
I just think if you represent whole SQL standard like this, you'll be all covered with hair or something.
Yes, okay.
Totally hairy.
So this was supposed to be internal. What I showed you in the slides supposed to be internal representation. Let me show you what actually you're supposed to use. So this was the original idea. There is a macro here that parses the SQL for you and spits out those type ugly syntax. But I didn't just show it because it's not the theme of the talk. That's it.
Thank you very much.
Welcome. Oh. Sorry? Oh, thank you. Oh, and the video is live now. That's this one. Cool. That was very quick.
Hello, thank you. I'm here to the left.
Oh, hi.
Hi.
Sorry.
Thank you very much for the talk. I have a small question. Can you please go to the slide when you actually defined your query with a type before you explained how it is implemented? Oh, I think it was in the text editor, how you actually wrote that query. Not in an example, but like the third tab. I think, yes, this one, and scroll a bit down.
Yes?
Yeah, here. So basically, you need to duplicate the whole query in the type definition and in the actual query, which is written in the string downside.
Yeah.
Yeah?
Right.
So there is no any way to avoid this.
I can. So it's fairly simple to also write type class derivation that generates string representation from the type. It's possible. I have all the information here. But what I'm showing you here is supposed to be the output of a macro. So you are supposed to write this. So there is no point of me just doing the derivation while I already have the string anyway. Just put it and duplicate the information. That's it.
Okay, thank you very much.
All right, welcome.